Uh, so we invite today Professor Ajit Mohan Srivastava from Institute of Physics, Bhubaneshwar. So he did his PhD from Syracuse University, USA. After that, he was a research associate at University of Minnesota, and then he was at University of California. After that, he joined in 1994 at IOP. And regarding his research contribution, he has significant contribution to the field of physics, in heavy-ion collision, topological defects, and cosmology. And also recently he has been contributing to astrophysics. And with this, also I would like to say that he, as a person, very easy to approach, and he holds a dynamic personality, and you can anytime go to him and discuss physics. He is happy to discuss with you. So with this, I would like to over to Ajit. So today he will be talking about investigating cosmic string theories in liquid crystal experiments. So over to Ajit. Please continue, Ajit.
Yeah, thank you, Mindy.
And
Yes.
one second. So I would like to request all the participants to mute the mic, and whenever there is necessity, you can unmute and ask questions. So that's so
Okay.
now, Ajit, please go ahead.
Yeah, thank you, Mindy. The talk will be for 45 minutes, right? And 50 minutes of questions. Is that right? And what's the
Yeah,
idea?
I mean, not necessarily hard bound, but
Okay,
yeah,
fine. Roughly that. Okay, good, good. No, because people have just attended a talk earlier, so I have
yeah,
no.
but we are late, so
Okay,
I don't know.
ठीक है,
Okay.
ठीक है. Okay, thank you, Vinity, for nice introduction. As I said, that it's always pleasure to be with the company of people at IISER Mohali. I feel at home. I hope I can visit there sometime again with COVID in enough control. So mm, this topic is actually is a very provocative topic, and a lot of people, many people switch off at this moment because they say, "What nonsense are you talking about? What is this cosmic strings and liquid crystal experiment? They have nothing to do with each other." So the purpose of the talk is to make you comfortable that it is indeed possible to not just investigate, actually test cosmic string theories in liquid crystal experiments and test them rigorously, quantitative tests. And that's what I would like you to be convinced about. So idea is the following. So we have a condensed matter system and there is a universe out there. And both things have these systems, universe and condensed matter system, have interesting phenomena occurring. My focus will be on phase transition, spontaneous symmetry breaking, and associated topological defects production. It's called cosmic string in the universe, and there are called like flux tubes and vortices in condensed matter system. So first, what I will do is because generally topological effects are not very familiar to people, so I would explain topological effects in a little bit detail, different type of topological defects. And if I can just succeed in that, that will be good enough for me. If you don't understand, if we don't have time for anything, that doesn't matter to me. Because I think these are very beautiful objects, and it's good to. I got hooked to them in my second year of PhD, and I've never left that love. So, and I would like to give a little bit detailed understanding of a string defect. And then we'll go to formation theories of topological defect and the theory of cosmic defect formation, which was given by Tom Kibble long time ago. And then we'll have the main topic of the talk, how to test these theories in laboratory experiments by focusing on topological defect formation in liquid crystal. This is experiments we have been doing on for a long time now. Uh, Two of my students got PhD in that topic actually, basically. And these are quantitative tests. And this is where the whole thing lies, that the two systems are so different. I'll tell you how different they are in number. So what universal properties? That is the trick here. Universal properties, by definition, depend on very robust quantities like underlying symmetries and space-time dimension, and nothing else. So that's what we'll be doing. We'll be extracting universal quantities on topological defect formation theory, And they are the same whether you have a cosmology or you have a condensed matter system. And we'll test those numbers. Things like universal exponents and things like that. So condensed matter systems and the early universe, there's a deep correspondence between the two systems. Most important thing being the spontaneous symmetry breaking, Higgs mechanism, phase transition. In fact, the ideas have been exchanged from condensed matter to particle physics and back and forth. We all know that. We know in condensed matter system, typically, when you heat a system, there is a restoration of a symmetry. And when you cool the system, there is a spontaneous symmetry breakdown. Very occasionally, it happens in reverse way, but almost always this is what happens. And low temperature phases many times allow for very interesting objects in condensed matter systems. There are vortices in superfluid helium, flux tubes in superconductors, and as I will show you, hedgehog monopoles and strings in liquid crystals, disclination lines in crystals. If there are condensed matter people around, they will know. And skyrmions, very interesting object. They have now become very fashionable because of quantum Hall system and condensed matter system, and they are very, very interesting topological objects. These are all examples of topological objects. So basically, spontaneous symmetry breaking transition can lead to formation of topological effects. And the early universe, two-slide summary of the relevant aspects of cosmology in the theories of universe. So universe is expanding, as we know, and means it was smaller earlier and denser. And in fact, long ago, it was very small, very dense, and very hot. It expanded from an initial condition of almost infinite density and cooled, reaching present situation, and the expansion still continues. This is, in a nutshell, this is the Big Bang theory of the universe. This is well established by now, especially with discovery and precision data from cosmic microwave background radiation. So the universe cooled as it expanded. Now, we are familiar in condensed matter system. When a system cools, it goes through phase transition. And sometimes these are symmetry breaking phase transition. So just like it, same thing happened in the universe also. We know the particle physics models of the early universe, and they tell us that just like in condensed matter system, the universe, while expanding, cooled and underwent several symmetry breaking phase transitions during its evolution. Some of these transitions are very similar to transitions like superconducting transitions or liquid crystal transitions. So now I'll tell you about topological defects in the early universe. Because there were symmetry breaking transitions in the early universe, they were associated topological defects, just like flux tubes and all that in condensed matter system. But their properties are remarkably different. So the universe, when it started, the earliest stage which we can talk with some confidence, earlier than that we have no idea because it requires quantum theory of gravity. But the earliest stage we can talk about is when the temperature was 10^32 Kelvin, and GeV is 10^19 GeV. The density was 10^93 grams per centimeter cube. And this was supposedly at a time which is 10⁻43 seconds after the supposed Big Bang age of the universe at that stage. You can just roughly call it. Though we don't know what actually happened during that time. So from this very large temperature, the universe expanded and cooled down to the present values. And look at the values now. 3 Kelvin temperature. From 10^32 Kelvin is 3 Kelvin now. And density to 10⁻29 grams per centimeter cube. That's the average density of the universe right now. And present age of the universe is 13.8 billion years. So during this expansion, the universe has undergone several spontaneous symmetry breaking phase transitions. And these transitions can lead to topological defects, just like flux tubes and monopole strings in condensed matter system. So their properties are very exotic. The expectation is indeed correct, and theories of particle physics predict there may be following types of topological defects. They're supposed to be a very good possibility of magnetic monopoles. These are point-like defects, the size of 10⁻29 centimeter, okay, but 10⁻16 times heavier than proton. Proton has a size of 10⁻13 centimeter. This is 10⁻16 times of that proton size, and 10⁻16 times heavier than that. Cosmic strings are line-like defects with a mass density of 10⁻16 tons per centimeter, and almost zero bit. Its thickness of this string is 10⁻29 centimeter. But look at the mass of this. Mass density of 10⁻16 tons per metric tons per centimeter. Domain walls mass density of 10⁻46 tons per centimeter square, metric tons per centimeter square. So compare here, the mass of the sun is 10⁻27 tons, A mass of a galaxy is 10 + 38 tons. So a micron size domain wall has a mass equal to mass of a galaxy. So clearly, if such domain walls were there in the universe at present, they will cause immense gravitational effect, and observations rule out such domain walls. But so actually, it's very interesting. This has been used to constrain various theories of particle physics. Any particle physics theory which predicts the existence of such domain walls is ruled out. You don't consider those theories. But monopole cosmic string can exist in the universe, and they're expected to form at very high temperature of 10^9 Kelvin. So it's important to understand the properties of these topological effects and their formation mechanism, because they will affect the dynamics of the universe in an important manner. So what is it? I mean, I've been using the term topological effect. What is a topological effect? So let's go term by term. Defect is exactly what it says. It's a localized inhomogeneity in an otherwise homogeneous system. That's all. You have a wall on the paint, and somewhere there's a bad painting. You always say, there's a defect in the painting. That is a defect. In condensed matter system, you always one atom gone, it's a point defect. But there's something different about this topological defect. So I give you an example of the first. Let's consider. So I will focus on system which exists in two different phases, thermodynamic phases. Thermodynamic phases, when you have separated by phase transition, you typically introduce an order parameter, which is different value. We take different values in two phases, typically taken to be 0 in one phase and non-zero in some other phase. So we call it phase 1 and phase 2. For example, water is steam. The order parameter is density here. It's almost 0 in the steam phase and non-zero in the water phase. Or superconducting phase transition. Superconducting phase transition is some of your, the order parameter is the Cooper pair, related to Cooper pair wave function here. So it's a complex number there. So there are different kinds of topological effects. There are point defect, monopole. So it would be something like that you have a water, say, in a bucket at 30 degrees centigrade, room temperature, okay? And you have a tiny steam bubble inside it. You will call it defect naturally. It's not a uniform water, there's a steam bubble. Of course, we also know it can disappear very quickly, but just hold on to it. A tiny steam bubble embedded in a bucket of water at 30 degrees centigrade temperature is definitely defect. Outside there is a uniform phase and there is. But now imagine that suppose you had a water and you have a tube-like region of steam, and water is still at 30 degrees centigrade temperature. You will say this simply is not impossible. You can never have such a thing. Steam bubble you can imagine, but you can never imagine a bucket of water, 30 degrees centigrade, and in which a tube of steam exists. And if I tell you there is a sheet of steam, which will be domain wall, this makes no sense because these things will disappear immediately. If you try to create a tube of steam, it will just disappear. There will be water everywhere. That is where topological defect differs from ordinary defect. If it was a topological defect, what happens is the water steam phase transition has an order parameter which is density, which is not rich enough. It doesn't have enough structure. So it doesn't allow for topology. Just defects. And just plain defects have no stability. They just disappear. If it was a topological defect, then they will have a tube-like region of a higher temperature phase embedded in a low temperature phase, and you can't do anything to it. The tube will remain tube, sheet will remain sheet, point will remain point. They simply will be indestructible. Topology protects them. So this is what showed the importance of. So the structure shows the origin of the word defect, because otherwise homogeneous system and some inhomogeneity. So a defect represents a localized region of one phase embedded in the background different phase. Localized region of steam in water. Why topological? I said these defects can be topological. So let's spend a few minutes on this term topological. Again, this term is not very familiar to some people. I mean, student age, you don't know about this too much quite often. So existence of these defects originates from topological considerations. What does this mean? In mathematics, a given property of a system is said to be of topological nature if smooth deformation don't change that property. I'm sure these days, because there is so much condensed matter physics being done, topological condensed matter, topological insulators and all that, everybody has seen the following diagram. A coffee mug being smoothly changed to a donut, and a regular cup, wine cup, smoothly changed to a sphere. Basically, you make it with a clay. You make it with a clay. And you can deform a coffee mug to a donut Idea is you don't create any hole, you don't close any holes. Rest everything is allowed. You don't close holes, you don't create holes. That's called not continuous transformation, not smooth transformation. Other than that, you can intuitively feel these things are possible. Converting coffee to donut. But this is a little hard. Basically, actually, in mathematics, topological quantities do not change under smooth deformation. And precisely in mathematics, topology relates to continuity of functions. You define topology on spaces because you want to define continuous function. That's all. You don't want to worry about differentiability of function. The moment you want to worry differentiability of function, you are not just talking about topology. You're talking about differentiable structure, manifold structure. But as long as you have a space, you simply say, I want to define continuous functions. You are talking about topology. So if a quantity depends only on continuity of functions and not on differentiability, then it is topological. So I'll give you a simple example. You take a rubber sheet. Rubber sheet always is a good example to use when you discuss topology. Line in that. This is the left hand side, the straight line. And do any smooth deformation. Literally smooth deformation. Actually, the smooth deformation I'm using intuitively, but this is a well-defined mathematics formulation. You can write down mathematical equations to define what you mean by smooth deformation. But for us, it is good enough that you stretch it and all those things without puncturing the thing. So you take rubber sheet and deform it. You see the line will change into various shapes if you deform it. It will change into curves and all that. So if differentiable structure is changing, you can see the derivatives of this function are changing. It's a constant derivative thing when you straight line, and it has all kind of derivative in you. But what you cannot do by smooth deformation is a changing of the straight line into a broken line. That is not possible. It will never happen. However, you deform the sheet, you can never convert a continuous line into a broken line, a discontinuous line. This is what it means topology. Topology will not change a continuous function into discontinuous function, but it will change its derivative. So if a quantity depends only on the continuity of function, then it will be invariant under such smooth deformation. That's what it means topological invariant. Topological defects are precisely those objects which remain unchanged. Their existence remains unchanged when you make such function remains, underlying function remains continuous. Basically, function we'll be dealing with the order parameter. Order parameter like density for water. So as long as the order parameter field defined at each point remains continuous, whatever else you do with this thing doesn't matter. You can change its values, but we keep it continuous, and the topological effect existence will remain there. It will not change. So topological defects are stable against smooth deformation, continuous changes. And this happens, topological defects arise when order parameter space has specific non-trivial structure. It's not like steam bubble in water, which can disappear by local cooling. Now, it should have more structure than that. Density is just a real number, and water density is not just real number, it takes only positive values. If there's a real number which can positive and negative value, you still can have topological effects. But a density which can only take real values, it's very hard to come up with examples where you can have topological effect. So we know that, I mean, this term may not be familiar to everybody, but you define what's called order parameter space. When you have a phase transition, you always define what's called order parameter space. In the low temperature phase or high temperature phase, whatever values order parameter takes in that phase is called order parameter space. So for example, in the low temperature phase or whatever phase, it's the lowest free energy, whatever value order parameter takes in the lowest free energy state is called order parameter space. Now, so the order parameter space will have a non-trivial structure only if it consists of several values of the order parameter. So suppose you have a phase transition in which the order parameter, you have a low temperature phase and order parameter has settled to lowest free energy value. If it has a unique value, there is no possibility of topological effect. That's what happens in water steam system. For every phase, water or steam, it takes a unique value, either in water or steam. So that's why you don't have any topological effect. It should have at least two values, or maybe a continuous set of values in any phase. Then you have topological effect. And if you know the definition of spontaneous symmetry breaking, this is precisely the definition of spontaneous symmetry breaking. That a ground state, the state of lowest free energy, the ground state, is basically, in this case, their ground state. See, typically your energy is the Hamiltonian, and if it has same values, while the order parameter is varying, then that means that the ground state is not invariant under a symmetry transformation. There is symmetry transformation because the energy is invariant under those transformations. So I'll give you examples so this will be more clear. So Ising model, everybody knows the magnetization density is m here, and the high temperature phase free energy plot I have given here. I have seen this thing that at T greater than critical temperature, the lowest free energy is m equal to 0, zero magnetization as a unique value. So high temperature phase cannot have a topological defect because it's a unique value. Low temperature phase, we know the magnetization can take the plus up value or down value, m0 and minus m0. So there are two values. And indeed, there is a topological defect in this case. These are called domain walls. Spontaneous symmetry breaking in high energy physics is very familiar, Higgs mechanism and everything. And so we have topological defects in high energy physics. What happens is that in condensed matter, when you discuss spontaneous symmetry breaking and topological effect, and you discuss in high energy physics, concepts are the same, but terminology is completely different. So I would like to just use this terminology. So I would like to use back and forth because I have to discuss cosmic strings and liquid crystals. So I have to tell you about these different. So in high energy physics, the order parameter is typically the vacuum expectation value of a multi-component scalar field, which we call the Higgs field. So wave of a Higgs field is what we talk about. And that is the order parameter what we use in the density or Cooper pair, wave function, etc. is the order parameter in condensed matter system used. An order parameter space, the values taken by order parameter in lowest free energy state is called vacuum manifold in high energy physics. Free energy, when we talk in condensed matter system, is the effective potential in high energy physics. So these are the difference in terminology, but otherwise concepts are absolutely identical. So this example, I would like to explain in a little bit detail. String vortices in superfluid helium, and identical discussion holds for U1 cosmic strings. So the normal phase and superfluid phase for helium are distinguished by a complex scalar order parameter. By the way, same thing applies, exactly same order parameter is also valid for superconductors. In that case, this complex order parameter is related to the wave function of Cooper pairs. Two electrons form Cooper pairs, and their wave function is related to this complex order parameter there. So psi equal to psi1 plus psi2. I'll write it like that. And psi would be the Higgs field in particle physics. Complex scalar Higgs field. So in normal phase, psi 0, superfluid phase. There is no superfluidity because psi represents actually the superfluid condensate. So mod psi square will give you in some sense density of a superfluid component in a superfluid helium. And psi 0 in normal phase, so psi is non-zero superfluid phase. Its magnitude gives the degree of superfluidity. So one writes down actually free energy density in this case. Again, you will call it effective potential for particle physics. For uniform psi, the free energy or effective potential will be written like this. Minus alpha of t times mod psi square plus beta times mod psi 4. Okay. Alpha of t depends on temperature. Is less than 0 for t greater than Tc or greater than 0 for t greater than Tc. This free energy is invariant under U1 transformation. Psi going to exponential I theta psi. This is U1 symmetry breaking. But this discussion is just look at the shape of this thing. So this is psi1, psi2 I have written. So this whole plane, psi1, psi2 plane is a complex plane, and any value of in the psi1, psi2 plane is allowed order parameter. This dashed curve is represents the free energy for a normal phase. And this is a curve, but actually it's a curve has a rotational symmetry because it's psi1, psi2. No? So it is it's a surface of revolution around this z-axis. So at t equal to greater than Tc, you see that psi equal to 0 is the lowest free energy. Z-axis is the free energy in this case, free energy density. And free energy density is lowest for psi equal to 0. Psi equal to 0 is normal phase. So T greater than critical temperature, the entire system is in the normal phase. There is no superfluidity. But what happens is that as the temperature is lowered through critical temperature, you see that now the lowest energy does not occur at psi equal to 0. It's mod psi not 0. Mod psi equal to eta. Mod psi equal to eta. Mod psi equal to eta, but this whole circle of values. Any value is allowed because free energy, you see, is mod psi square plus mod psi 4. It does not care about the phase of psi complex number. It only depends on magnitude of that. So the phase is undetermined here. So free energy is exactly the same for whatever be the phase, and any phase is allowed in this case. This is what is your familiar case of spontaneous breaking of U1 symmetry in this case. And this, we will say, this gives you rise to vortices in superfluid helium and U1 Gaussian strings. So what, let's realize what we have is, we have a system now in superfluid phase. So T is less than critical temperature. You are in superfluid phase. That means psi and temperature is fixed. Once temperature is fixed, mod psi has precise value eta. Eta is depends on temperature. You fix temperature, eta is absolutely fixed. So eta is fixed, but theta is not fixed. So let's consider the following. So I have a physical space in superfluid sample, and this whole thing, this left part is a superfluid phase. Ignore the curve and arrows right now. Yes, yes. Now I draw a hypothetical curve, closed curve in this case, the green curve, hypothetical. Green path, I just closed path I consider. It's in superfluid phase, so everywhere I have to give you value of order parameter. So I'll say, well, mod psi is eta. I'll say, no, just you don't give me mod psi. Order parameter is psi, not mod psi. Order parameter is complex number. So you're giving me mod psi, but also tell me what is the phase. It can be anything, phase can be anything. So now let me give you a possible variation. This can be anything, it can be just a constant, phase can be constant in the entire region, but I'm giving very specific kind of variation. You can ask me how it arises, but that we'll discuss later. That's the theory of formation of defect. But suppose it is like that as I go along the closed curve, as I go along the closed curve here, the theta varies in this manner shown by the arrows. These arrows angle from x-axis, you can imagine, is giving the phase of psi. Phase of psi, of course, is an internal quantum number, in internal value. I'm denoting here as an angle in physical space. It's not an arrow in physical space. It's a phase of a Cooper pair, wave function. But suppose angle made by this arrow from x-axis denotes the theta. And suppose varies like that. You see something very special is happening. As you go around the closed curve here, theta is changing by 2 pi. The vector is rotating. So the phase of psi is rotating by 2 pi. It's very special kind of variation. Now, if this is true, then something very special happens. I say I shrink the curve a little bit. In this case, I have shrunk it a lot, but very tiny amount. Very, very tiny amount. If I shrink the curve by infinitesimal amount, theta everywhere should change by infinitesimal amount. That's the meaning of continuous function. Theta is phase of order parameter. Order parameter is continuously defined. And you remember my discussion of topology. I keep the things continuous. Everything is allowed as long as you maintain continuity. So I will change the curve slightly, and because continuity is maintained, infinitesimal curve cannot change the angles by jump because this is a continuous function. So if angle everywhere changes by infinitesimal amount, delta theta equal to 2 pi should only change by a infinitesimal amount. But it's a delta theta around a closed curve. It cannot change by any number less than 2 pi. Because a vector rotates around a closed curve either by 0 or 2 pi or 4 pi or minus 2 pi, minus 4 pi. Discrete. Net rotation of a vector around closed curve is either 0 plus minus 2 pi plus minus 4 pi. So the delta theta is stuck. If I shrink the curve by slight amount, net delta theta is stuck to be 2 pi. And then I got it. Now I just keep shrinking curve by tiny, tiny amounts and make it smaller, sufficiently small. Delta theta is stuck to be 2 pi. I make it very, very tiny. Very, very tiny. Make it almost zero size. And then I have a trouble. Because zero size, but delta theta is changing by 2 pi, theta has become discontinuous. Theta has become discontinuous. I am forced to conclude, so a loop of zero size and theta changing by a finite amount is a discontinuous thing. So I am forced to conclude that if the phase of psi was changing by 2 pi around a closed curve, large closed curve, when I shrink the curve down to zero size, theta becomes discontinuous either where I have shrunk it or somewhere before that. I have assumed in this case delta theta remains 2 pi because theta remains continuous. But if theta doesn't remain continuous, then they all bets are off. Main point is there is a discontinuity of theta included somewhere. Theta must be discontinuous somewhere inside. That is a topological defect. Just by knowing a curve, large curve, a theta variation on that, I have, without knowing anything inside, in a superfluid phase, I have concluded that theta must be discontinuous somewhere. That discontinuity is a topological defect. That will be vortex. This is the winding number 1 defect because the delta theta change by 2 pi. You change by minus 2 pi, it's an anti defect. You change by 4 pi, it's a winding number 2 defect. So now, but there's the free energy. I told you the free energy is minus alpha mod psi square plus beta mod psi 4 for a uniform order parameter. But if order parameter is changing in space, now we concluded that theta has to change. It becomes discontinuous. You should include gradient of psi term also. Psi is not just constant. Even if mod psi is eta, so phase is changing. And there is a problem. The grad psi will act on phase as well as on amplitude, magnitude of psi. So what happens is that if you keep the magnitude fixed to be eta and only change the phase becomes discontinuous, grad psi will diverge. Grad psi will become infinite. You can't allow that. The only way to do is magnitude becomes 0. When psi magnitude is 0, then theta is ill-defined. It can be discontinuous. Psi is equal to mod eta exponential I theta. If eta is 0, theta is ill-defined. So the only way to get away from the discontinuity of theta and diverging free energy is you conclude that psi must vanish somewhere inside. Now, okay, I have gone fast on that, and my apologies for that. It's a very loaded set of statements I have given. So I am sure some students would have had difficulty with the argument. I myself had difficulty with the argument. Please think about this argument later on. And then you'll, right now, just trust me, that a large loop in a superfluid phase on which hypothetical closed path on which the phase of order parameter varies by 2 pi or integer multiple of 2 pi, not 0 multiple, you have to conclude that psi must vanish somewhere inside. And that is very interesting. What is psi equal to 0 inside? You recall this phase. This is the free energy plot for temperature less than critical temperature. We had a superfluid phase. So free energy plot was this as you are supposed to be living somewhere here in the valley here, lowest free energy in the entire superfluid phase. But what you have concluded is somewhere there is a point, at least a point, maybe more point, at least a point where psi is 0. But psi equals 0 is high free energy. High free energy. Psi equals 0 is normal phase. So you see, what you have concluded is that if you have a superfluid phase everywhere, you thought everywhere, and you drew a closed path hypothetical, and you found that theta is changing by 2 pi, you are forced to conclude that in center somewhere there is a point or a region where the system is in the normal phase, which is the high temperature phase. Temperature is not high, but the phase corresponds to thermodynamic high temperature phase. Temperature is what you are given to it. Temperature cannot change. This is exactly what I told you in water stream system. If water stream system allows for such thing, you will have a water 30 degrees centigrade, and there will be steam bubble, and you can do nothing to it. It will be always there, and it will be a 30 degrees centigrade temperature. In 2 dimensions, it will be topological point defect. But see what happens in 3 dimensions. So I have a 3-dimensional sample, and I drew a closed path on a plane. I do a closed type path in a plane here. But when I was saying to make this path smaller, nobody told me that I have to make this path plane. I can make it smaller a little bit up and then shrink it, little bit up, then shift it, little bit up. Wherever I shift, wherever I shrink it, I have to conclude there psi equal to 0 somewhere inside. Wherever I shrink it. Now again, you think about it. The only way to get to make the whole thing consistent is there must be a string of zeros of psi enclosed in this loop. So this is even more remarkable. What I have said is that you have this closed path in a superfluid sample on a 3-dimensional sample. On simple this closed path, you concluded that there is you found out that theta is varying from 0 to pi. You are forced to conclude there is a string-like object on the entire in which the psi equal to 0, there is a normal phase. It will turns out it is a tube-like region, very thin tube-like region in which the helium will be in the normal phase. not in the superfluid phase. And you can see this phase, this string cannot end. If the string had a finite length, then I could take this, suppose the string ended here, then I could take this, and after that there was superfluid phase. Then I could take this loop and shrink it outside this end of the string. But I can't do that because even there I should find psi equal to 0. So the string has to go from end to end of the sample, or it should be closed loop. This is topology at work. So this is string is related to what's called first homotopic group. Those people who know, and there are other homotopic groups, second and third homotopic groups, all those things. So the same thing happens in liquid crystals, and that is the topic of my interest. So liquid crystals are orientationally ordered liquids. They're formed by elongated molecules. These molecules are typically 20 angstroms in length and about 5 angstroms in thickness. One kind of molecule. There are variety of, they're disc-shaped molecules and all those things. So I've given you this kind of molecule. This is what we have used. Sorry. So you see on the right-hand side, the microscopic picture at the angstrom level, the molecules are completely randomly oriented. This is the high temperature phase. When the molecules, the thermal energy is so much that they get randomly oriented. You cool it a little bit, and they tend to align along their length. This is what is shown on the left side here. This color coding is that is showing the orientation. So their yellows are pointing in one direction, but this orientation can change slightly. They are called liquid crystals because they are orientational, because they align in some direction. So there is orientation with them. Liquids don't have any orientational ordering. And they're liquid because these molecules flow actually. They flow exactly like liquid. So you see, because there is a flow also in this case, and also the orientation can change. Brown has a little bit different orientation, green has a little bit different orientation. So this is defined, this orientation is defined by an order parameter called director. There is a magnitude of this, magnitude of ordering, how much they are ordered. So magnitude of ordering will mean 0. This is 0 ordering here. This is called isotropic phase. High temperature phase called isotropic phase. There is no ordering, so you'll say order parameter has 0 magnitude. It's called S, I think. So order parameter strength is called S equal to 0. S is not 0 in the low temperature phase, and it has a direction called director. But you see that these are long molecules. They don't arrow. They're not arrows. Like our complex vector had an arrowhead. It was complex vector, complex number, so it was a vector. But in this case, these are just ellipsoidal molecules, ellipse-shaped molecules. So they don't have any arrowhead. So that makes the entire whole thing very different. So it's not an arrow here. It is not a three-dimensional arrow in 3 dimensions. It's actually a segment, a line segment, or you say arrow with double arrowhead. And that allows for topological effects. What happens is, earlier I told you, you take a closed path in which the arrow changes from 0 to 2 pi. Here, arrow doesn't have, because opposite directions are identified. It doesn't have arrowhead, so you can just change by pi. But along a closed path, this line segment is again stuck. Net variation has to be either pi, 2 pi, multiples of pi. Now it doesn't have to be multiple of 2 pi. Multiple of pi because it can point opposite and there is no arrowhead on there. So if you consider a situation here where around a closed path, the arrowhead here, it goes back to same direction. It changes by pi. You'll conclude there is a string defect in the center. A string defect would mean what? A string defect would mean isotropic phase. This is the high temperature phase I told you, and S is equal to 0. So basically what's happening is that orientational ordering here, in which the orientation changes by pi, when you consider smaller path, orientational ordering cannot be maintained, because you at the smallest possible loop, you cannot suddenly change by pi. Only way is that you don't have any ordering at all. So you go to isotropic phase. Isotropic phase, and this is called nematic phase. The ordered phase is called nematic phase in liquid crystal. So the ordered phase and the isotropic phase have different optical properties. They're different refractive indices. So when you shine light through them, they appear differently. That's what I will show you. You will see that thing. In fact, it is not just that. It's very interesting because these molecules, they are rotating in physical space. So as the light passes through, suppose you have polarized light, then the polarization properties are, suppose you put a cross polarizer, you have a polarizer here pointing in x direction, you put your liquid crystal sample and put another polarizer which is crossed with the bottom one, 90 degrees. Then what you will see is, if there is a point defect like that, something like that, actually not this one, but something in which the director rotates by 2 pi, you'll see 4 lines, 4 dark brushes here. So this I'll take time to explain, so don't worry about that. Basically, just imagine this, that these liquid crystals have very special property. They're birefringent. That the refractive index depends whether the electric field vector is pointing along the direction of aligned molecule, or perpendicular to it. Molecules are aligned in nematic phase. So whether the electric field vector of polarized light is pointing along that or perpendicular, the refractive index is different. Phase, there is no such alignment, so it's a unique refractive index. Because of that, when you are in the nematic phase, when there is a director order parameter orientation varying from 0 to 2 pi, you get these dark brushes. And this crossing of these brushes is a bright point you see. Bright point is the isotropic phase. You can see the contrast. Remaining thing is grayish in color and darkish in color, but this point is 0. The crossing of this is bright because it is isotropic phase. So you see that at low temperature liquid crystal phase, you have trapped a point of a high temperature phase, the isotropic phase, just like I told you earlier. This is again a topological effect. So now I mentioned to you there's a whole different variety of topological effects. In condensed matter system, you have topological effect with a free energy, which is dependent on temperature, and it carries out phase transition at room temperature typically. The liquid crystal, which I use for my experiment, has a phase transition at 36 degrees centigrade, and literally room temperature. That's very, very convenient. That's about 10 to the minus 3 electron volt if you convert to electron volt. For nuclear physics, there are fermions, which correspond to 1 GeV free energy, and 10 to the 16 GeV for defects in the early universe. Completely different, whole different ball game altogether. So the objects are completely different, but what they mean, the classification, formation, and correlation of defect, because the underlying ideas are topological. And using those universal features, we are able to test them. So I should tell you this thing, that cosmic strings were very exciting long time ago. They have, as I told you, mass of 10 per 16 ton per centimeter, so very strong gravity. And long time ago, it was believed that cosmic strings gives you rise to structure formation. The large string loop will accrete matter around it, or strings moving through plasma, cosmic plasma will cause over density fluctuation. That will give you clusters of galaxies and all those things. Micro background radiation data ruled out that possibility. It says that actually density fluctuations came from inflation, not from cosmic string, but it doesn't rule it out completely. A very small fraction can still be due to cosmic string. People are trying to constrain it. But more importantly than that, many high energy particle physics models of the early universe predict cosmic strings. You really don't have a choice. They are there. There is no way to avoid them. So if these cosmic strings are there, can you see them in the sky? And indeed, the observational, there are very important, very interesting observational evidence is possible for cosmic strings, and people are spending a lot of for that. There are some evidences in terms of double images of distant galaxies, but really interesting thing is the gravitational waves of cosmic strings. These cosmic string loops, they oscillate, and while they oscillate, they emit gravitational waves because they're very heavy. These gravitational waves have very characteristic signatures. And there are experiments which this is the LISA, Laser Interferometer Space Antenna, which is planned, I think, in 2035 to go to space, where it is like gravitational LIGO, Virgo, everybody knows. We detect a gravitational wave, which have this 4-kilometer long arms. These are supposed to be million kilometers away. These 3 satellites, they're supposed to be million kilometers away, and they'll basically be just like LIGO, Virgo. And this is the official poster of LISA. Several years ago, it was there. And I'm very proud of this picture, so I want to show it to you. This official poster had 4 pictures. And this is These are possible sources of gravitational waves which LISA can detect. Supermassive black hole binaries, numerical simulation. Compact object captures, again, numerical simulation. Galactic white hole binaries, numerical simulation. The last picture, I'll zoom here, and this is what it is. Cosmic strings and phase transitions. The top two pictures are from a numerical simulation by a group, Bate and Shellard, and bottom two pictures are from our experiment in IIT Bhubaneshwar. This is the only experimental picture in the whole poster. So we are quite proud of that. I'll show you the video and pictures of this thing. Now, correspondence of cosmic defects with condensed matter system is really very remarkable, because cosmic strings have velocities or speed of light, close to speed of light. Liquid crystal strings move with few microns per second. You'll see that. I show you a video, you'll see them moving, and there's few microns per second. And this is speed of light in cosmic strings. Early universe is relativistic quantum field theory, general theory of relativity is applicable. In liquid crystal, classical statistical mechanics apply. You don't even need quantum statistical mechanics, classical statistical mechanics. No gravity, obviously. So how do you relate the two systems? How do you test one system then? And as I said, you focus on universal quantity. So maybe I'll skip this part, because so universal quantity will be the following. Let's first focus on theory of formation of defects. How defects form? I drew a very funny kind of phase variation. I said to draw a hypothetical closed curve in which phase is varying 0 to pi. Why should it vary 0 to 2 pi? It costs energy, so it should just be uniform. Lowest phase energy order parameter with a uniform phase. Why should it vary at all? And that too vary in a manner that you have 0 to pi variation. That's what I want to explain to you. People routinely saw in condensed matter system topological defects form. Why do they form? So earlier people thought they form by temperature fluctuation, thermal fluctuation. Bose-Bond factor, exponential minus E defect by KT. E defect, topological defect energy, loop or whatever, what is centimeter pair, divided by KT. Soon it was realized, later it was realized that this mechanism is not the dominant mechanism most often in phase transition. It happens in some cases. Costello-Thouless phase transition is one where this is the one which controls the dynamics. But most often in phase transition, this is not the dynamics. Dynamics is by non-equilibrium mechanism, which was actually proposed by Tom Kibble for cosmology. Now it is applied routinely in condensed matter system. And that concept is very simple. So I'll explain to you by considering example of a first order phase transition. First order phase transition is something, it's like water to steam phase transition. What happens is you make a phase transition by bubble nucleation. Lower temperature phase, you cool the system. Low temperature phase happens in terms of bubbles. So for example, if you have this is what your fog is there, when you have a water vapor in the sky and you cool sufficiently, temperature is cooled, then water droplets form. There's a cooling of the system. So in the form of spherical bubbles. Same thing here. So you have, I drew this Psi1, Psi2 again. Superfluid helium does not have a first order phase transition. I should warn you. Helium-3 had a first order transition, but so let's just consider a case. In cosmology, they are often first order phase transition. If it was first order transition, the diagram of free energy will be the following. High temperature will remain the same. So psi equal to 0 still is the lowest free energy and no superfluidity. But low temperature will be, it was earlier like this, but now there is a little bit dip in the center. Lowest free energy still is there, psi equal to eta. But at psi equal to 0, there is a little bit of dip. And what can happen is that if you gently cool the system can get stuck there. But it wants to come to lowest free energy. But it can't come because there is a barrier. So what it does, it hops through the barrier. It can't hop through the barrier in the entire sample, because that much energy is not available. So it hops through the barrier by small bubbles. That is why first order phase transition always proceeds through bubbles. Tiny bubbles will hop and you have a low temperature phase in there. But that happens very interesting. So now in this case, we have a complex order. A complex order parameter has an arrow. When mod size equal to eta, complex order parameter has arrow. So look at this. In the lower thing, I have formed this. I have created a situation when there is a first order transition happening. Psi equal to 0 outside, you have normal phase, say normal helium phase, and you supercool it a little bit, and the bubbles of superfluid phase will occur. So these are bubbles I have drawn. Now inside the bubbles, mod size equal to eta. But not just mod psi, I have to give you phase. Phase has to be given some value. So I drew these arrows. But now you can realize that what arrow points in one bubble and what arrow points in second bubble have nothing to do with each other, because they don't even touch each other. They are far away. Inside, in between them, psi equal to 0 with theta is ill-defined. So different bubbles have different values of phase inside. This is obvious. You can't avoid it. How phase transition proceeds is bubbles expand and they collide. But then this funny thing will happen. When the bubbles meet, expand and meet, now you have got these bubbles which were carrying arrows which were pointing in different directions. So you see, I was telling you that lowest free energy will be constant phase everywhere. It is impossible to achieve in a phase transition. First order transition, I gave you example. Second order transition, same thing happens because there is a correlation volume. So you trust me on that. But first order transition is, you can see, because each bubble is in the beginning had a different phase, and when the bubbles meet, they carry this random variation of phase from one to another. So Kibble simply said that that's what it is. A phase transition proceeds by either a domain formation or a bubble formation. Each bubble or domain should be assigned with a random value. Issue is what happens when the bubbles meet. What value would you like to choose in between? So Kibble made a very simple approximation. He said you would like to minimize phase. So have a smooth variation of phase which has a least variation. That's called technically called geodesic rule. So basically you avoid too much variation. The smallest possible variation. You have to vary. You don't no choice. Very smallest possible variation. And then now there's a funny thing, because you see, let us look the particular example here. These three bubbles, when they have met and you allow a very smooth variation of arrow in between, you will get the bottom picture. This is the vortex. If you go in a closed curve, arrow is varying by 0 to 2 pi. It has occurred there, it has formed there, you don't have a choice in that. And some places it can form anti-vortex. So vortex, anti-vortexes will form, you don't have a choice in phase transition. Same thing in liquid crystals. I have given you isotropic phase outside in a sample, and you have formed the nematic bubble. First, liquid crystal actually is first order transition. I'll show you video, you will see that. Tiny bubbles will form. Have a molecular orientation which is random from each other. So they form, and then you will eventually, this is what will happen. You see, the different bubbles will meet, and as they meet, the molecular orientation varying randomly from one bubble to another bubble, and you will get springs in between. So this is the experiment which we have done, and I should tell you that the first experiment of this kind was done by Bell Labs and Princeton group. This is the reference: Chuang, Durer, Turek, and Yerke, and in Science in 1991. And they actually saw that liquid crystal formed these strings, and they studied the evolution of the string network and corresponded it to theory of evolution of the string network in the universe. It was a very beautiful experiment and very motivating, but it was not a quantitative experiment. Quantitative experiment in the following sense that the correspondence could not be established quantitatively. They studied scaling exponent and all that for the string different, but that depends on the dynamics. It's not a universal quantity. What we did is we actually tested the theory of defect formation by calculating the probability of string formation. In fact, I remember when these people had given talk, I had asked Neil Turek that this is a first order phase transition. Why don't you simply count the number of bubbles and calculate the, oh, by the way, here, so you see what you have got is the phase transition completed when the bubbles have met. When bubbles have met, the bubble size is fixed. Each bubble has random variation of order parameter. So all you need to do is take the number of bubbles, random variation of order parameter, and simply calculate mathematical probability of what the probability of forming 2 pi or minus 2 pi, etc. You get a probability of defect formation. Probability of defect formation will depend on what? What is the symmetry here? And the number of bubbles in the bubble. So if I normalize the whole thing by bubble size, the only system information going in bubble size, if I calculate probability of string formation per bubble, it doesn't depend on anything which depends on system. It depends only on the symmetry, what is the order parameter, and the dimension of space, which is 2 dimensions. It's a universal quantity. So probability of string formation per bubble normalized to bubble size is a universal quantity. So that's what I told you, that this is a universal quantity, you can measure it. So what he told me was that their experiment is a quench experiment. They have a pressure quench cell. So they don't see bubble. They only see suddenly a lot of strings form. I'll show you quench experiment also in our case. So carried out experiment very carefully. This was done in Syracuse University. Mark Bovik, L. Chandar, and Eric Schaefer, my collaborators. This was published in Science, 1994 paper. And what we did is we didn't have a pressure quench sector. We did something very simple. We realized that it's a very weak first order transition. You cannot do anything violent to it. You should do it very gently. So we put a liquid crystal open droplet on a glass slide and gently heated via lamp, low wattage lamp, very gently. And we saw bubbles. And we saw and with microscope we studied it, and we saw the bubbles, and we counted bubbles, and this was our picture of bubbles. You see, these are bubbles. These are nematic phase. You see the contrast. Nematic phase has a dark thing in the background is the isotopic phase, and the bright things are bubbles of nematic phase. They met, and you get the strings. These are the strings. So we simply counted the length of the string by putting the thread around it, and we didn't have a computer software at that time, and counted number of bubbles and took the ratio. And the number was in fantastic agreement with the theory. This was our first experiment. This was the first experiment we had done, and this verified the theory of cosmic defect formation. This is the picture from experiment done at IUP Bhubaneshwar, because now we had a much better system here, much better quality microscope. So you see the bubble formation. You cool system of bubbles form, and you get a dense network of strings. I'll show you a lab setup. I think Ambrish and Minati have seen it probably. So this is the microscope. This is a glass slide on a droplet on that, and heat by a lamp. That's it, and you record it. At that time, okay. So I'll show you. Now you'll see isotopic. Hello?
I have a question. So does the evaporation effect, does evaporation play?
There's no evaporation in the liquid crystal. Evaporation temperature is very high. So at 34 degrees, nothing happens. It's a very thick liquid. Liquid crystal is very thick liquid, so nothing happens to it. No evaporation. Okay. Yeah. Okay. So what I'll show you now is that I'll have a sample. You'll see a little bit dirt on that. So don't worry about dirt. But the phase transition will happen. You'll see bubbles of nematic phase occurring, and there's a string, and the string system will evolve. And you'll see how they evolve. So this is right now isotopic phase, and a lot of these dots are the dirt, because it's an open sample. And we are cooling it very gently, and you see these are bubbles. Bubbles form, they met, and these form the strings. And you see strings are shrinking. And very interesting thing you will see, when strings cross each other, they pinch off at the crossing point. You see the loop formed there. And the loop shrink and disappear. This is exactly supposed to be dynamics of cosmic string. I'll show you a different picture in a quench. This is the kind of quench which Turek and Yarke and these people did in Bell Labs. And so that's why they couldn't see the bubble. This will be a quench. We made a fast variation of temperature. They made fast variation of pressure. You won't see bubbles here. So you see. It's a fast change in temperature and the bubble. Again, you will see lots of places where the crossing strings cross, pinch off there. This is supposed to be a very important part of dynamics of cosmic string. So Turek and Yarke sector had studied this evolution of the string network. But that actually is dependent on system dynamics. It depends on viscosity, depends on whether they cross each other, whether they pinch off, and all those things. But string length per bubble is a universal quantity. Then that was done in Syracuse. Then we did this experiment here we set up the lab in Bhubaneshwar, and we asked a different question. We asked, so suppose I don't do 3-dimensional sample, I do 2-dimensional sample. Then there will be vortices. These will be point vortices. If there are point vortices, there are vortices and anti-vortices. If there are vortices, I can ask this question, that I take a finite region of that sample. How many vortex minus anti-vortex number is there? It's like a net charge, net topological charge, vortex minus anti-vortex. Now you can imagine sort of if the total number of defect, anti-defect is n, and they are randomly distributed, then delta n should be something like square root of n, because n is randomly, points are distributed. So it will be square root of n. This is something very beautiful happens here. that this is the underlying order parameter here, complex scalar order parameter. Because of that, one can show that in this case, the delta n will vary at n power 1/4. Now, net number of defects. So this is a closed loop I draw. Inside with a lot of defects and anti-defects, vortex, antibiotics. I ask what is number of vortex minus antibiotic delta n, that will go as n to the power 1/4, not at n power 1/2, which will vary. This is a characteristic prediction of cable mechanism for topological defect formation. When they randomly form, this will happen. Not for all systems. When they form randomly in a phase transition, this is what happens. This is the underlying idea here, that each domain has a random variation of order parameter from one domain to another domain. Then you predict this. And once you predict this, this is the universal exponent. This is a critical exponent. This is universal. And we verified this in our experiment. Oh, okay. So what you check is this. When you carry out the experiment and you plot, you take small pictures in which you have certain number of n defects, and take small portions in which total number of defects is roughly n, say 10. The small portions every time is a 10 or 20 or 30, and you for 10 defect and defect system, you find out what is delta n, and you plot a histogram of that. It will be histogram centered around 0, because you can have sometimes more vortices, sometimes more anti-vortices. Its standard deviation is supposed to be n power 1/4. That's the point. So standard deviation of those Gaussians is predicted to be n power nu, where nu is 1/4 is the prediction of cable mechanism, and otherwise should be 0.5. C is not a universal quantity, so don't worry about C. We find universal exponent to be 0.26 plus minus 0.11 experimentally. Remember, if it was random distribution, it will be 0.5. And cable mechanism prediction is 0.25. And we found it 0.26 plus minus 0.11. This was our experiment. Again, same thing, a glass slide on which there is droplet here. And there is a cross polarizer. Cross polarizer is very important because that helps us distinguish vortex versus anti-vortex. String domain, when you take C string, you don't know whether it's string or anti-string. But when you see point vortices, you see those brushes. And those brushes, you do something very important. You rotate the sample while doing the experiment. And the way brushes rotate, you can figure out their vortex or anti-vortex. It's a very beautiful thing. I showed you, here it is. These are the brushes, and what you do is you rotate the sample while doing the experiment, and brushes will rotate one way or a different way for a vortex anti-vortex. So that's how you identify, and you count vortex anti-vortex. It was very we took about 1 year in completing the analysis in this case, literally. And this was the plot. So n equal to 10, n equal to 10, we had lots of data set. So n equal to 10 is this star plot, 20 and 30, and we fitted Gaussian without fixing the center of the Gaussian also. Center of the Gaussian and the width was randomly varied. And we plotted that sigma. These are the 3 values of sigma with errors in this. And as I told you that we got the value 0.26 plus minus 1. This was very good experiment, I believe. This is the first critical exponent which was measured of a cosmic defect. It is a cosmic string. Nothing to do with, nowhere it's relevant that it is a liquid crystal system. This could be very well cosmic string, because we are just simply talking about number of defects in a domain. Then, of course, there are more things there. Density correlation functions, and you can calculate, and these peaks. The peak position is universal, that also we have verified. I want to close by just in last. I want to close by one thing. Because we wanted to do more things, so we were thinking that I mean, primordial black holes in the universe, they evaporate. No, primordial black holes, they evaporate, and when they evaporate, they can heat up the plasma around it. Hawking radiation, they can heat up. So we've had this idea that they can heat up the plasma around it, so they can be symmetry restoration. When they symmetry restoration and then further cooling, you can form cosmic string. So we wanted to check it. So we just tried the following. You took a liquid crystal droplet and tried to heat a small part of that by putting this. You can see this wire. This is the wire. So this was a wire. It was 100 micron wire. And we tried even 10 micron. The first time I saw 10 micron wire, you can't see by your eye. You have to use a lens to see. So 100 micron wire thickness and coupled to a battery to heating it. and you bring it close to the droplet, hoping that you are heating a localized region, something like emulating a black hole, and it forming. So ultimately, I became so impatient, I dipped it inside liquid crystal, and something very beautiful happened. So I'll show you the picture of that. So this is the central thing is the end of that thing wire, and you see small current, small heating. You see these loops coming out. These are loops of string, pneumatic liquid string. Now I'll show you another now larger current in this case. You see these string loops are forming and getting thrown away by convection currents. So this actually gave us very good idea, and we wrote a paper on that later on. That same thing can happen in the universe. That a black hole evaporating can heat up the region around it, and convective flow will throw strings around. These strings can form together, join together, and form junctions. Now, I don't have time, so I would like to, I think, stop here. But we have continued this work, and we have worked on other things. Duality between point defect dynamics and string dynamics. Or maybe let me just show you one thing. Yeah, these are nice pictures to show you. Look at this picture. No, they're shrinking beautiful. And another picture. And you remember I had shown you earlier the cosmic string, the liquid crystal string evolution. That doesn't look like that. Strings evolving. What is happening is I have a point vortices, and these brushes are not string. These are director variation. But it has very good similarity with the string. So what we ask the question is, do these brushes between the strings, which is just a variation, behave like strings? So we have established actually duality between the two point vortices and a three-dimensional string network. So okay, I think I'll stop here because I have taken extra time. I think, sorry. Okay.
Okay. Thank you very much, Ajit, for the interesting talk. So I would request participants, if there is any questions or you can go ahead.
So, I don't have a question, but Ajit, I was just interested in knowing that whether you are continuing this experiment further.
Yeah, this is latest experiment.
Yeah.
That will be of interest to you. Latest experiment will be of interest to you. This is the setup I have just made. You can see this is the motor here, and there is a thin wire coming out. This is actually optical fiber. And on optical fiber, there is a coating of liquid crystal. The idea is this, that the coating of the string, liquid crystal, will have a string formation. So a string will form and will wind around this. What I can calculate is, in this case, how much is the string binding per correlation length. This is supposed to see cosmic strings can wind around any extra compact direction. If there is extra compact direction in the universe, the cosmic string can wind around that. So its tension would not be that of a space without compact direction, because winding is like a spring now, right? So you would like to know its tension. For knowing its tension in when there is compact direction, by knowing how much it winds around it in a general phase transition, how much it winds around compact direction. How do you know that? So by this experiment, I can actually check how much string winds around in a compact direction per correlation length. It will be universal quantity again. So using this, I can tell you how much is the effective string tension for extra dimension theories of string, cosmic string.
So does that actually depend? Like, so how do you know about the number of compact extra dimension in this
I don't
case?
know. I don't. So for each compact direction, it will happen like that. Just a minute. Yeah. So for each, it will wind around like that. So if there is one U1 direction, it will wind in that. If there is two S1 directions, it will wind in two directions independently.
Okay.
Completely independently. So one direction, when I calculate, the calculation applies to all directions independently.
Okay. I see.
Yeah.
Thanks.
Okay.
I have a question.
Yes.
So you were talking about the gravitational waves emitted by the cosmic strings.
Yes. Yes.
So are there any observation yet?
No, no, no. That LIGO Virgo cannot detect gravitational waves from cosmic string. The wavelength is very large for this, so you can only
That
detect by Lisa.
Lisa is supposed to be.
Lisa is going to pick up that.
Okay. Okay, thanks.
Sure.
So, are there any more questions? So, I don't see any more questions.
Okay.
So, let's finally thank Ajit for the interesting talk.
Okay. Pleasure. Thank you. Okay.
Thank you.
Bye. Bye, everybody.
Bye.
Sure. Yeah.
Bye, Ajit.
Bye. Bye. Yeah. Sure.
Bye.
Bye bye.
Bye, Charanjit. Yes. Bye, Harbin.